I'm Pasquale and I'm second year BM. And tonight we will discuss some of the some problems and exercises that are part of your exam tomorrow. And of all the topics, so first of all structures, then functions, and then sequences and series. I started from not so difficult exercises. So as you can see, the first one just says that if we have an structure which is open and B which is compact, what we can say about their intersection? So A intersection B. Well, first of all, we have to remember that, of course, one is open. One is open. So what does it mean that one is open? One is open means that the intersection for sure cannot be closed, because the intersection also comprises the part of the set which is open. And of course, it cannot be, of course, also closed or bounded, because meaning that it's compact, we know that B is of course closed and it is bounded. So we cannot say that this set is of course open. It cannot be closed. So we can just, first of all, we can say that compact, so the first option is not possible because it's closed and bounded. And since A is not closed and not bounded because we don't know, we cannot say that the intersection A intersection B is compact. Then what can we can see that it's not for sure also B, because of course it would be open if and only if also B would be open. But since it's compact, so it's closed, of course we cannot admit that the intersection is open. And we also exclude, by the same reason, the D option, that is closed. Why? Because of course the point is that B is compact, okay, so but A is, and so it's closed, but A is open, and so the intersection cannot be closed. So the only option that we are left with is the C. So the A intersection B. Can you listen to me now? Okay, I think so. Um, and just the point is that if you need, if you ask me for something, simply ask me wherever doubt you have. uh I think some. Okay, sorry, 1 second. Okay, and I will go so for the second exercise, which is about the Demorgan's law. And so first of all, we know that we can see the Morgan's law are that A intersection B complement. So we take two sets, and the complement of the intersections, or the intersection of the two sets, is equal to A complement union B complement, as we all know. And also we can remember that A union B complement is exactly equal as A complement intersection B complement. And these are the Morgan's law, and we can apply them in order to solve this exercise, because this exercise is simply asking which is the, how can we write this set in a different way. So we simply can write that A intersection B complement complement is equals to, well, the like there is an intersection, so it's really similar to the first Demorgan's law that we have written here. And simply the point we have to consider is that, of course, there is a B complements instead of B. So that will be, instead of having like a B complement, we will have simply a B. And so we can simply write that it is exactly equal to A, according to this law over here, it's exactly equal to A complement union B. So the correct answer for this exercise is, of course, B, because it's simply the Morgan's law. So nothing more than the Morgan's law. And that's it. If you have questions, as I said before, like, don't hesitate to ask me. And otherwise, we go on, and yeah, like with the third exercise about the first chapter, so the structures, and we can see that in this exercise, simply we talk about the R3 Euclidean distance. So this is the topic, and we want to like establish the distance between a certain point, and the origin, and we want to know how much is this distance. But like, it's simple. Maybe you have studied it also in high school, so it's not that difficult. To find these distance r, we can just write the square root of, we have to calculate the distance. If we want to calculate every kind of distance in R3, we just have to calculate the square differences of the points. So also in this point, we just can calculate, for example, like in this case, it's -3 squared, because it's 0 the other portion of the point of the origin, plus, in this case is 4 squared, because it's 4 minus 0. So we can write 4 minus 0, but it's just 4 as here. And also we can write 2 minus 0 squared, and it will be simply equal to the square root of 3 squared, that is 9, plus 4 squared, which is 16, plus 2 squared, which is 4, and we end up with a square root of 29, which is exactly the first answer. So also for this exercise, like the answer is not that difficult, and we just can apply a formula with the points we have for every kind of exercise like that, and it's the same both in R3, but like if it would have been, for example, in R2, it's completely the same, just we don't have 3 points, we don't have x, epsilon, and z, because here we have x, epsilon, and z. Instead, with R2, we would simply have like the x and y, and it's the same exact formula. Then we move to the following topic, which is function, and also maximizers, minimizers, and like global or not. And just I took this function, which is it's piecewise defined. So it's defined in this way when x is less than 0, while is defined in this other way when x is more than 0. Like the best way to cope with this kind of exercise, in my opinion, is to draw the functions, because drawing the function, you can understand, of course, if it has maximizers, minimizers, or like these kind of things. And first of all, so I would start like drawing the, I will start drawing the simply the Cartesian plane, and of course we try to together to draw the different functions. For example, when x is greater than or equal than 0, we have that the function is the absolute value of x minus 1. But having a function which is the absolute value of x minus 1, we can just simply use the function x minus 1. And if we want to study the function y equal to x minus 1, just we have to draw it. So when x is equal to 0, of course y is equal to minus 1, and when y is equal to 0, well, x is equal to 1. So we just draw, and we know this is of course x, this is y, and just when we have x equal to 0, we will have a point here minus 1, and so a point here to draw the function. And when y is equal to 0, we will have x equal to 1. So first of all, if you want to draw x minus 1, it will be this the drawing of the function. But of course, we know that we have to draw draw of course the absolute value of x minus 1. So simply we have to put this portion of the portion which is under the x-axis. We have to put it upside, like by symmetry. So this part would be like this, the same exactly. While this the part that is under the x-axis, we have to put it like, sorry, we have simply to put it like this way. Oh, sorry again. We simply have to put it this way, if I can. Okay, this way, and like this is exactly 1, and so this is the first of course function, the one in which x is greater than or equal than 0. Of course, this function would have a minimizer at x equal to 1, but we have to consider of course also the other function. So how to do with this other function? We just draw also this one. When x is less than 0, we analyze, and we know that of course this is x, the absolute value minus the absolute value of x plus 1. Oh, sorry, just have to. Okay. I'm not so good with the iPad, sorry. And just we have to like the y in this case would be equal to minus the absolute value of x plus 1. So first of all, I would like to draw the x plus 1 simply, and when of course x is equal to 0, y is equal to 1. When y is equal to 0, x is equal to minus 1. So in this case, when x is equal to minus 1 over here, y is equal to 1, so here. So the first function would simply be this way. But then we have to, of course, put the other way. Like we have to say to do the same thing as we did before. So to put the part which is under y upstairs, and so simply this part is exactly the same, while this part is like as this shape. But we also have to consider that, of course, this other function has the minus in front, the minus before the absolute value, and so we simply have to put another time the same effort to do exactly the same thing as before. So the function, the final function would be this, and this. Okay, so we just see that in this case also the point is that also in this case we can see that there is no global maximizer. Why there is no global max? So the correct answer is of course C, because of course we can see like a not global maximizer, a relative maximizer, which is exactly like this one, because it's the maximizer in this area. And as like same, we can see also a minimizer, a relative minimizer, which is exactly this one for this area. So each of the functions, of course, has a maximizer or minimizer if we consider it like by themselves. But if we consider the piecewisely defined function, and so the entire function here, we see that it has neither a maximizer nor a minimizer, and so simply we have to answer that there are no maximizers in this case. Then I go on with another exercise. Well, this exercise is not that difficult. We just consider the natural domain, so the ranges of the functions. And we consider both of the of both the functions. First of all, so I would start with the first one. So we consider A, and A is the natural dominion of f of x equal to the square root of x plus 3 over x minus 3. So we just write f of x equal to the square root of x plus 3 over x minus 3. And that's the function, sorry. Now we want to calculate the natural domain of this function. But how to calculate this natural domain? Well, it's not that difficult, because we all know that in this case the only the problem that we have, of course, is the square root. So is the square root. And so we have to consider that there is a limitation for the square root function. And what do we have to do when we have a square root function? We have to put everything which is inside the square root function. So in this case, x plus 3 over x minus 3. We have to put it always greater than or equal than 0. So x plus 3 over x minus 3 is greater than or equal than 0. And we can just study the sign of the function over here, and it's like x plus 3 greater than or equal than 0, while x minus 3 greater than 0. Why do we have to put, why here there is the equal sign and why here is not the equal sign? The problem is simply that we have the denominator and the numerator. In the numerator, of course, it's easy, because in the numerator we can put every value which is also equal than 0, because if we have the numerator equal to 0, we don't care. It's exactly the same thing as having because it's 0 that can be equal to 0, of course. But in this case, instead, it's completely different, because in this case we don't have the equal sign, because x minus 3 cannot be equal to 0, because if x minus 3 is equal to 0, of course x would be equal to 3, and if x is equal to 3, we will have 3 minus 3, and so we will have 0 at the denominator. And if we have 0 at the denominator, of course the function is impossible, it doesn't exist, so we have to only put the greater sign, and we solve. We go on, and just we know that x is greater than or equal than minus 3, while x is greater than 3. And we can do also the sign, and just it's minus 3. Oh, sorry, no. Again, here is minus 3, here is 3, and simply, okay, if we have to study the sign, okay, if we put x greater than or equal to minus 3, we will put continued line here and not continue one here with this point which is included. So we put a complete a mark here. Instead, if x is only to be greater than 3, we just put the continued line here, while here is discontinued. And here we put an empty bullet, because of course it's not included. So we just have to sum the signs, because if I put a continued line, it means plus, while if I put this continued line, it means minus. So it's a minus here, a plus here, a plus here, minus here, plus here. And if we just add up the signs, we know that minus times minus is plus, minus times plus is minus, and minus and plus times plus is plus. So since we have greater than or equal here, we just can establish that here and here we have to consider to calculate this range, this dominion. And so the A would be exactly equal to x less than or equal than minus 3, with and also x greater than 3. Here, again, there is not of course the equal sign, and this is the range, this is the natural dominion of this function. So all the values that x can have in these functions, in this function, are of course or either are less than or equal than minus 3, or they are greater than 3. And we can start by doing the other function in order to see what is the relation of between the range of one function and the range of the other function. we can just do the other function natural domain g of x, which is equal exactly to like square root of x plus 3 over square root of x minus 3. And of course, in this case, it's not, we don't have to we don't have to study the sign. We just have to do the system, the normal system. So not the sign system, but the normal system. So we say that x plus 3, also in this case, is greater than or equal to 0 because of the square root as before, while in this other case, in the denominator, it's in the numerator, so we can keep the equal sign. Instead, in the denominator, 1, we just cannot keep the equal sign, but we have to put everything just x minus 3 greater than 0. And in this case, we do another kind of system. So simply we can say, like we can do it like that. Sorry. We can do like that, and we write minus 3 and 3. Of course, this would be that the first one would be that x is greater than or equal than minus 3. So a line here included. And instead, in the second one would be that simply is x greater than 3 with an empty bullet point. And in this case, we just have only to consider the part that they have in common. So it's just this part that we consider in the range. So the range, the natural dominion of B would be simply equal to x greater than 3. So this is the natural dominion of B. This is the natural dominion of A. And we can say that, of course, x greater than 3, so the 3 positive infinite. In this case, instead is, of course, minus infinite, minus 3 included, united to 3 positive infinite. And just we can say that, of course, this is included in this one because there is 3 positive infinite, and also here we have 3 positive infinite. And so the only answer that can be left here is that, of course, B is included in A. So B is a subset of A, of course, because we have seen that it's like a subset of it. And that's all about also the the functions. If you have other further requests and things like that, you can ask me whenever. And then we have another that were exercises simply, while now we have a sort of proof that is included in your exam as well. And we have to prove, of course, that, as we can see, that they are both monotonic, or that they are both monotonic to function. If the function are, if f and g are both monotonic, then also their product f of x times g of x is monotonic. But how can we prove it? We can prove it if and only if we know a theorem which states so. But as far as I remember, there are no theorem which states that that if two functions are both monotonic, well, also their product is monotonic. So if I don't remember, if you in the exam you don't remember how to do a theorem, maybe it doesn't exist simply. And if it doesn't exist, it's even better for you because you don't have to prove it. You just have to prove that it doesn't exist, providing a counterexample. Okay. So I just choose, I think about, for example, two functions, which can be whatever. For example, simply, really simply, f of x equal to x and g of x equal to x minus 1, for example. We have to check, of course, that our hypothesis. So the hypothesis are that all the f and g are both monotonic. How can we say, of course, f of x is monotonic because it's just the bicept of the first and the third quadrants. And we have to check also that this one is monotonic. Sorry. And we can check simply that it's monotonic because, of course, we know that if we want to draw it really good, simply we do that when x is equal to 0, well, y is equal to -1, and when y is equal to 0, occurs x is equal to 1. So this is x and this is y. When x is equal to 0, y is here, -1. When y is equal to 0, x is here, 1. And so it's exactly this the function. Oh, sorry. I want to be more precise, but okay. And that's the function. So of course it's a monotonic, because what do we mean by like a function to be monotonic? It means that the function is either always increasing or always decreasing. So both in these cases, of course, we have that we have two functions which are both like always increasing. So when x increases, also y increases. They are strictly increasing, both of them, and so they are monotonic. But what do we want to establish? That f of x times g of x is monotonic. We want to prove the contrary by a counterexample, and this could be like a good counterexample. But why? For example, we just study that f of x times g of x is equal to x times x minus 1. So it's exactly equal to x squared minus x, okay? What is this? It's a function we know, so we can draw it. Oh, no. Oh, okay. Sorry. It's x squared minus x. And it's a function that we know, okay, because it's a parable, but like it's a curve that we know. So simply we can try to draw it. What do we have to know to draw, for example, this kind of curve? If we want to draw this kind of curve, a parable, we just have to know like the point, the most important point, which is like minus minus b in the actual formula over 2a, which is like the x of the verts. And exactly it's equal to minus 1 over 2, sorry. If you want to be really precise. And so, no, sorry, again. And so it's exactly 1/2. And it's here, 1/2. And then if we want to find also yv is equal to, simply we substitute 1/2 into the function, it's 1/4 minus 1/2, so it's minus 1/4, and it's exactly here. So the point is here, and since we have a positive number, we have 1 here, actually, like the curve is like the as positive is concave, so we can draw this graph, and we can just understand easily that it's not monotonic at all, because like monotonic, as we said, is always increasing or either always decreasing, while this function is like in this part it decreases, in the first part it decreases, while in this other part it increases. So it's impossible for the function to be monotonic. Maybe it can be monotonic only in this range and in this range, because of course here it's always decreasing, here it's always increasing. But like the exercise asks for a theorem, so it should be valid for every function, functions. And as we have found like function which don't behave accordingly, we just say that we provide a counterexample for the function, and we just like told ourselves that the function, that the theorem is false, and so we have proven it. We can't just say for example in an exam, we just say okay, it's false because I don't know the theorem. No, you have to prove it, providing a counterexample, as you have been told a lot of times for sure. And otherwise, if, for example, it's valid, like you find examples, you don't, for example, if you think that there is no theorem like that, okay, and you want to find a counterexample, if you try like twice, 3 times, and you find always that the for example the theorem is valid, well, in this case, maybe just you don't remember the theorem. That's easy. So like try, if you do like two or three examples which are valid, it's like probable that you don't remember the theorem simply, which could be acceptable. Okay, and now we like simply go over and we arrive to the third the third topic of the evening. What an amazing evening. And mm, we talk about sequences, and for example here they are giving us a sequence, this sequence, and they want to know how can we write like the sequence in another way, and we have to like establish how to write it. First of all, they are giving us the a0, and they're giving us the an. So the first thing to do simply is to find like the how much is a0. So if we substitute a0 here, like in the an, we have to substitute simply 0 to n, and it's like 5 over 2 to 0. So it's 5 over 1, and it's equal to 5. So for sure, the two options that are remained are B and D, because we have 5 here and we have 5 here. Now we have to like find the other way to write it. Okay, if we just try, let's try with a1, for example. A1 is equal to 5 over 2. Okay, and instead, for example, a2, just from this formula, is equal to 5 over 4. A3 is equal to 5 over 2 to the third, which is 8. Okay. Now we just want to know which is the correct one, if it's this one or if it's this one. And easily, if we want to do it, we can just substitute. It's the fastest way to do so. In fact, like an in the first case, like we can just try. In the first case, an would be equal. Sorry. In the first case, an would be equal. For example, a1 in this case is equal to 1/2 to like 1, which is 1/2, times 8 to the n minus 1, which is a0, okay? And a0 is 5, so it's 5 like over 2. A second is equal to simply 1 over 2 to the n, which is 1/4, times like a1, which is 5 over 2. In this case, we find that it's simply 5 over 8. So we already find that there is like something that doesn't go, that it is not going so good. So we try to the other for the other one, which is this one, the D1, the fourth one. And we can like understand simply that in this case, A2 is equal, for example, what A1, of course, like A1 is equal to 1 over 2 to 1, like times an minus 1, which is a0, which is 5, so it's 5, like 5 over 2 as well. But a2, for example, is equal to 1/2 times an minus 1, this one, which is a1, so times 5 over 2, which is 5 over 4. And so we have like already, we can see that this is the right answer because it's the only one left actually. But if we want to try more, we just can calculate also a3, which is equal to 1/2 times 5 over 4, which is 5 over 8. And so also this one and this one are the same. And so we can like finally conclude that of course the right answer is the D one. And so we also like we have resolved easily this exercise. Of course, if you have something to ask me, I recommend you That's tomorrow the exam. So that's your last choice. Well, and let's go over with limits of sequences. Actually, when I was in high school, I did before with functions, but I don't know why they do like that in Bocconi. But okay, it's the same basically. Okay, that's a limit we have to solve. Of course, it's not that easy. Like we see that it's a little bit tricky. Mm, but simply we know some like some fixed theorems for limits, some fixed notations for limits, and for example the one we can use here is not that difficult. We just have to learn it because otherwise, yeah, it would be difficult. Because in general, we know that the limit. Oh, I want to change color actually. I want to be more. The limit as n tends to positive infinite of 1 plus 1 over x, for example, over 1 over n, sorry, because I'm used for functions, 1 over n to n is exactly equal to e. Okay, do you know e? Like e is a number, you know for sure. It's 2.71, etc., etc., etc. And that's the like this limit is always like that. If we want to apply it for example, the this exercise, it's easy. It's really easy. Why? Because we just have to make a little bit like some changes. Because we have a 2 over here, okay? So if we have a 2 over here, the nice thing, we just have to apply a mathematical trick. Because like if we have a 2 over here, it's the same of this one, of this one, if and only if we put like a 2 over here. But how can we do so? Well, it's easy because we just write that the limit as n tends to positive infinite of 1 plus 2 over n times n, or like to the power of n, and we can easily, really easily, because we are allowed to do so, we put a 2 over here in order to apply this theorem, and then we multiply by 2, because by mathematical laws we can do so. We can multiply and divide the same number, like for the same number, so that like it's the same, it's always n, but just we use it to use this theorem. And of course, like we can understand that this factor, like all this factor, tends to e because of this theorem. So like it's not that difficult to understand it, that it is tends to e, because it's exactly the same, because it's 1 over n and it's 2 over n. Here is n and is n, like it will be n over 1. So it's exactly the same. It's exactly the same thing. And so this one tends to e, and then we have another, like we have the 2 over here. But what do we do with this 2? We just use it to put it here. So the final result of this exercise is e squared, and so we have c as the final option for this exercise. That was not that difficult. That was easy, but you should just remember the like these notable limit in order to do so, in order to do this kind of exercise. And now, before going on, we just do another proof, because you need it for the exam, as I told you. And it's like it's not that difficult once you have understood how to do so, because at first glance it could seem like it's not that easy, but actually it is. We have to use they are telling us like they tell us we have to use the comparison criterion. So which is the comparison criterion? We know that the comparison criterion just tell us that if we have three functions, or in this case sequences, which like are an less than bn and less than cn. So bn is the central sequence. we can know also that, and if we know that, for example, the limit as n tends to positive infinite of an is exactly equal to the limit as n tends to positive infinite of cn is equal to L, for example, whatever number it is, what can we know? We can simply understand that these are the hypotheses of the theorem, and I think you are so good at proving it so well because you are required to do so in the exam. So I'm sure you know it very well. But the point is that here we arrive to the conclusion to this thesis that, of course, we know that also the limits as n tends to positive infinite of Bn, of course, is equal to L. Because if this one and this one are equal to L, it starts like these sequences sort of comprise the sequence inside. So in fact in Italy they call, like in high school, but also also here the theorem of the due carabinieri, because of course it just says that they comprise the central function inside. But okay, apart from all this stuff, let's do the exercise because that's what we are supposed to do. So how would you start this kind of exercise? It's not that, like, the point is that it's a difficult function actually. Like, we cannot know it by substituting, for example, positive infinite here, because it would be like 5 over infinite times -1 times infinite, which doesn't provide any answer. Also because, as we know, -1 is not bound, like it's bounded, but between, like, it's not that good when we put positive infinite, because it doesn't give us an answer. So what can we do? We can consider like exactly the -1 function. Okay, -1 times all at the power of n, because that's the only thing we can actually do considering this function. How can we deal with this function? Well, the point is that we know, like everyone has to know this, that, like, really everyone, that -1 to n, like if we substitute to the n every kind of number, like every kind of number, 1, 2, 3, 4, 10,000, 11,000, whatever number, of course it can only has two values, which are like -1 or 1, because like -1 to the power of whatever number is either -1 or 1. So the function -1 to the power of n is bounded, and it's exactly bounded between, like, we can do it in another page. -1, sorry, it's too large, I write too large, I know. -1 to the power of n is always between -1 and 1. Okay, now the point is that we have to simply understand that here, for example, we have to multiply everything by this other quantity. Okay, so 5 over n plus 1. If we multiply 5 over n plus 1 times 1 minus, like, -1 to the power of n is greater than or equal than -1 times 5 over n plus 1, because we have multiplied it times 5 over n plus 1, and here we have the same, is 1, because there was here, times 5 over n plus 1. Okay, so this quantity here, this quantity here, this quantity here is just multiplied, because we can multiply, of course, this for the same quantity if we have like this kind of object here. So simply we can apply. Why can we apply the comparison theorem? Because simply here, this would be really, sorry, I want to change color. Okay, this would be an, this would be bn, and this would be cn. Okay, if we have an here, like, we can apply the limit as n tends to positive infinite of an, which is -5 over n plus 1, is simply is simply the same because it's a number over an infinite, so it's 0, okay? And this would be the limit of an, okay? Why? The limit of bn would be n as 10 tends to positive infinite would be the limit of 5 over n plus 1, which would be equal to the same as before, so a number over an infinite because n plus 1 is positive infinite, and so it's 0 again, bn. For the theorem we have stated before, so for the comparison theorem, we can just say that, of course, also the function which is inside the other two functions have exactly the same behavior. So also this one tends to 0, and so we can say finally, we can prove finally that the limit as n tends to positive infinite of 5 over n plus 1 times minus 1 to the n is exactly equal to 0, as we were asked here. So we have proved this idea with the comparison theorem. I think that's really important, just because last year, I'm second year, so last year when I did the math exam, it was one of the questions I had similar. So in my experience, you should study this well, and you should be able to do, it's not a matter of studying, it's just a matter to do mathematical tricks, mathematical applications and things like that. So just I'm sure you have done a lot of exercises, so you will be able to do it, don't worry. And then I would pass to the last topic of the evening, also because it's late. We have spent a lot of time together. You will study for sure also after my my lab, and I will study as well for my subject. So let's go on. The sum of the series, okay? So we want to we're talking about series, we're talking about sums, and so we want the sum of this series. What kind of series is it? It's simply a geometrical series. So a series of the form positive infinite and n equal to 0, q to the n. Okay, this is simply the structure of this kind of exercise. Now the q is, of course, q is equal to 2 over 5. What can we say about this kind of result? We know that the sum of q to the power of n is exactly equal to 1 minus q to n plus 1 over 1 minus q. Okay, this is the formula for the sum, and you should know it well because it can be asked for sure. It will be asked for sure because they love geometric series. I don't know why, but they love geometric series. Now, just easily, we want to calculate the sum of this one, of the result here. So simply, how can we do so? We do exactly this formula, and we say that the sum, I better another page, the sum of it was 2 over 5 if I remember correctly, the power of n, as we n equal to 0 to positive infinite, is exactly equal to 1 minus q to the power of n minus 1, n plus 1, sorry, 1 over 1 minus q. Okay, so it's simply 1 minus 2/5 to exactly n tends to positive infinite, so it's to positive infinite, over 1 minus 2 over 5. Okay, but what changes here? What do we know about this this function, not this function, this number? Okay, what do you think should be the value it tends to? If a number normally is raised to the power of course, positive infinite, what happens? It happens that the number tends to positive infinite. But in this case, it's different because we have a fraction here, and this fraction is not if a fraction is as the numerator, which is greater than the denominator, 5/4 or 3 over 2, this kind of fractions which are raised to the power of infinite, they would tend to positive infinite. But if instead we have another like we have, for example, function like 2 over 5 or 3 over 4 or 1 over 5, they will not tend to positive infinite because the denominator, which is raised to the power of infinite, will grow faster than the numerator, and so all these functions will tend to 0 because the denominator raised faster than the denominator, raised faster than the numerator. So it's easy to understand that, of course, it tends to 0 because it's a number over an infinite, which is 0. So going back to this exercise, I hope all is clear. Really, I really hope it, because I want your exam go well. And so this would tend to 0, as we said here, and it would be 1 over, like 1 minus 0 over 1 minus 2 over 5, which is equal to 1 over 5. If we want to do every passage, is 5 minus 2, and it's equal to 1 over 3 over 5, which is equal to 5 over 3. But that's not over, because if we do this exercise well, okay, I did everything good, that's the result. Oh, also here I have the 5 over 3, okay, that's good. Why not? Because that's the formula, I apply the formula, and that's it. But no, that's not the correct answer, in fact, because we have to be really careful of everything that they give us, because we maybe don't have seen here there is an n equal to 1, okay? And that's really important, because actually the n equal to 1 means something. Like maybe we can think that it doesn't mean anything, but actually, yeah, it means something. And what does it mean? It means that we start from a different kind of number. We don't start from n equal to 0, which is here in the formula we study here, and also in the formula we did here. So it's always like n equal to 0. We have to remember it. Instead, they asked us for this result. So it's not 5 over 3. It's actually, this is the result, okay, 5 over 3. But the point is that we have to put like 5 over 3 minus the 2 over, no, it was 2 over 5, yeah, 2 over 5 to the power of 0. So it's 5 over 3 minus 2 over 5 to the power of 0 is simply 1. So it's easy. 3. 5 minus 3 is 2. So the final result of this operation, put exclamation points. I love putting exclamation points. Is 2 over 3. So it's exactly the C answer, the right one. So this was tricky, but you should know it. You should know this. They put a lot of confusion. They want to do it so because they want us to be really careful about the exercises and all the things. So be really careful about every exercise and be really careful about everything they propose to you, because there could be trickies, because Bocconi wants to put trickies in exercises, but just to let you think more carefully and to be more careful about what you do and about what you have to do. This one, in fact, is really similar to the one. This is the last one, actually. And this is, unfortunately, and this is really similar to the one we did just now. And how can we do it? Well, that's the series, and this series just is as geometric as the one before. So we have to apply exactly the same formula, but there is like a 3 over here, okay? So we just have to, for example, write like that, as n equals to 1. Also in this case, consider the n equal to 1, and positive infinite. We can put the 3 over here. Like we can put it outside the sum, like, because it's useless to put it inside. So I put it outside, and the formula is exactly the same. So it's 1 minus q to the n to the power of n plus 1 over 1 minus q. Okay, and in this case, we do it now because it's faster. We like subtract from this formula the value of 3 times 1 over 5 times like times of course the power of 0, because we have subject the n equal to 0 and equal to 0, and we go over. We simply go over, and it's not that difficult, because actually it's really easy, because it's the same as before. It's just exactly the same, and we put like 1 minus here, that is it is here is simply 0 as before, over over 1 minus 1 over 5, and it is all multiplied by 3, minus 3 times 1, so minus 3, and it's equal to 3 over is 5 4 minus 3, which should be equal to is 15 over 4 minus 3, which is equal to 4. 15 minus 12 will be 3, and is 3/4, which is exactly the first answer. Oh, sorry. Is exactly the first answer. And so we just have done it. It's exactly the same. We just have to remember that here we have a 3, and we have always to remember that, of course, here we have n equals to 1. So nothing more difficult than the previous one. Well, okay, I try to do my best. I chose some exercises, not that difficult, not that easy, some more difficult than others, and just I want to thank you for being here and for listening to me. If you have anything, any kind of request, ask me. I left also my contact here. So it is my Instagram contact. This is my name, and really for everything you need or you will need, just ask me. Just send me a message. I will be really helpful in every situation. I want also to say thank you to Meetup, and because that's a nice thing to do. And that's it. So have a nice evening, guys, and I hope that tomorrow you will do well. It's your first exam, and you must do well, actually. So let me know if you want to always scan your exam, and that's it. So simple, like if you have any kind of questions, just ask me, and that's okay. Have a nice evening. Also now, if you want to ask me something, so